Today we're going to look at a different special factoring pattern that is known as a difference of two squares. And so with respect to vocabulary, which is what we're going to start with, when we talk about a difference of two squares, remember that a difference is the result of subtraction. So if I were to write an expression like a minus b, this would be considered to be a difference, right? What would be the opposite of a difference? Well, that'd be a sum, something like a plus b, that would be a sum. But we're talking about differences of two squares, okay? And so what's the other part of the vocabulary here? What's this idea of a square? Remember that a square is it's kind of a nickname for the result of a product of a factor with itself. So that is to say, like if I were to take a factor a and multiply it by itself, we tend to write that as a squared, but it just means that we have something squared. So when we talk about a difference of two squares, we're really talking about expressions that look like this: a square minus a square. And the reason why this is such a common pattern is because of what happens when we multiply what we call conjugate factors. And so the last part of a vocabulary review here is just what do we mean by conjugate factors here? What is a conjugate factor? Well, conjugate factors algebraically are considered to be a couple of binomial factors, but they're identical, you see. The only difference is that one is a sum and the other one is a difference. And the fact of the matter is, anytime we multiply two binomials, which we can kind of accomplish with FOIL, that are conjugates, okay, what we're going to do is we're going to start with our first here, and you'll notice that because these are both a, we're going to get a times itself. In other words, we're going to get a squared, so there's our first square. And as we go through our rest of our FOIL here, so the outer two terms, a positive a times a negative b is a negative a times b. And if we do our inner two terms here, we get positive b times positive a, that's ba, or we could write that as ab. And then we'll do our last two terms, a positive b times a negative b is a negative b squared. And so one thing I want you to notice that happens algebraically, and this is kind of a guaranteed thing to happen, is that we get the same product on our outer as we do on our inner. It's just that they're always different by their signs, and so they cancel. And what we get left with is the fact that we got the first part of these binomials squared, so the a squared in front, and then it's minus this b squared right here, or in other words, the last part of our binomials here, excuse me, squared. So we get this difference of two squares. And so really the idea is going to be that anytime we spot an expression that is two squares in a difference, okay, and order matters here, is we're going to get something that looks like this: a plus b and a minus b, where a is really just what we can square to get this first term in our difference, this first square, and b is what we could square to get the second part of this difference here, this difference of two squares. So let's go ahead and take a look at a few expressions that I might expect you to factor. But it says right here, factor the following expressions completely. If not factorable, then we're going to write prime. So letter A, this would be kind of really cookie cutter here, but I notice right off the bat that it has two terms, okay? And then it looks like they're both perfect squares. X squared is a square of x, and 9 is a square of 3, and it's a difference. Everybody looks happy here. Now, one thing I'm going to recommend you do before we factor this is really look for a GCF first, which is kind of common practice, but you'll notice that there's no GCF between these two terms. So the way this works is, man, we set up our binomial factors that we know we're going to get. We know that they're conjugates, and really the idea is going to be, well, what is like our a here, or our first term? So it would be whatever I could take times itself to get x squared. Well, that means that I'm going to have to put an x in front of both of these, because x times itself is x squared. And what can I take times itself to get 9? Well, I can put a 3 here. And it would be really easy to check that these factors work. Just go ahead and FOIL them back out. But this would be our conjugate factors here, okay? Looking at letter B, again, we always start by scanning for a GCF. And again, I notice there's no GCF other than 1. But these both look like it's got two terms here. They're both squares. X squared is a square of x. 16 is a square of 4. But it is not a difference of two squares. So just to be clear, I'm going to write that this is a sum. But because this is a sum of two squares, what we do have to write over here is that this is prime. So it's worth noting here that you cannot factor a sum of two squares. A squared plus b squared is prime. And the reason why is because if you were even to try, okay, to take like a plus b times a plus b, you would get a squared, right? You get your a squared. You'd get plus AB, but then you'd get a plus AB here, okay? And then you'd get a plus B squared. So you do get the A squared plus the B squared, but you also get this middle 2AB that's kind of something that you can't shake off, okay? And again, even if we try to do like A minus B times A minus B, again, you would still get your positive A squared in front. You'd get a minus AB and a minus AB when you complete your outer and inner multiplication, and you'd still get your positive B squared. You needed a positive B squared, but again, you get A squared minus 2AB plus b squared. So you cannot shake the fact that you have this middle term here when the signs on both of these binomials are the same. So that is why we can't factor a sum of two squares. So don't let me catch you doing that, okay? Letter C here, kind of similar. No GCF other than 1. It's got two terms. And the weird thing here is you might be saying, well, you know, this is to the fourth. This is not a perfect square, even though 16 is a square, x to the fourth is not a square. But, you know, you have to stop and ask yourself, could I take something times itself and get x to the fourth? And the answer to that is, well, certainly we could. We could take x squared times itself. And so that's what we're going to put in front here. We get x squared and x squared. One is plus, one is minus. And what could we square to get 16? Well, I could do this with a 4. So one thing that I'm always going to push you to do is to continue to look for, can I break this down any more? The reason why I didn't really try over here is because these x's were both to the first, and you really can't break down a first degree factor. But over here, these are both to the second. So it's worth my time to say, could I keep going on these? And you know, it's looking like this is a sum of two squares, and we just talked about this. So I'm going to have to kind of leave that alone the way it is. That's a prime factor, but this right here, this x squared minus 4 is a difference of two squares. And so we're going to rip it apart. And this would be an x in front. I could square x to get x squared. I could square 2 to get the 4, and one of these would be plus, and one of these would be minus. So here's our completely factored expression here, our product of prime factors, okay? And so this last one, letter D, this is just kind of to drive home a point that you always look for a GCF first. This might be looking like something that isn't a difference of two squares, but it really is something where, if you look at this, 12 and 27 both have a common factor of 3. If I take the 3 out first, I get left with 3. And on the inside here, 12 divided by 3 is 4. I get 4x squared. And then 27 divided by 3 is 9. I get left with this two-term or binomial factor that is a difference of two squares. And so I'm going to get 3 times my conjugate factors here, so 1 plus 1 minus. And what could I take times itself to get 4x squared? Well, I could take a 2x times itself. And what could I take times itself to get the 9 here? I could take a 3. And, you know, I should always check to see if I can keep factoring, but a big red flag that probably not is because these are first-degree factors here. So here's our completely factored expression, a product of primes. So I want you guys looking for differences of squares. Always make sure you check for GCF first. And you know what? Never can we factor a sum of two squares. Cheers.